Thanks for coming out. I'm Zach Murphree. I'm the Vice President of Technology Partnerships at Velo3D. Here to talk to you a little bit today about metal additive manufacturing and its role in production. I know that this is a pretty common theme in metal additive manufacturing, the transition from prototyping to production. And I have a little bit of a different twist on it today. Hopefully find it interesting. The transition's been happening over the last 5 years, and there are a number of companies that have done this very successfully. If you look at, as an example, medical orthopedic manufacturers, they've been able to go from prototyping parts to printing thousands and thousands of parts per year. There are some good examples in aerospace too. If you look at kind of the canonical metal AM part, the GE fuel nozzle, this is a part that has transitioned from prototyping to production pretty successfully. These parts all have one thing in common that you might not have considered before. They're all relatively small when you think about it. And there are specific challenges that come with transitioning large parts to production that these small parts are avoiding just due to their size. So one of the things I want to talk about today is the challenges with producing large parts and really transitioning those to a production setting. So if you look at kind of the history of metal additive, people have been selling metal AM systems for something like 20 years now, right? EOS released their first system in the late 90s, and the first industry to really take on metal additive is rapid prototyping. And in rapid prototyping, the goal is to print essentially one-off parts so that they can be used for form, fit, and function, and can be assessed a lot of times for different manufacturing processes at the end of the day. So the systems that were originally developed are kind of moderately sized 10-inch cube machines with one laser. And as parts started to grow and become more production ready, the machines grew. And people scaled these single laser systems to make bigger parts. That's certainly one way of approaching it, but the problem with these single laser systems is that they're really slow. If you're printing a really big part with a single laser system, it's just slow. The throughput is not high enough. And when you look at the total cost of a metal additive part, almost all of it is in print time. That is the majority of the cost of the final part. So this is a problem as you're transitioning to production because the parts are just too expensive for large scale production. You also have some capacity issues. There aren't that many large format single laser systems in the market. So if you're making a big aerospace part and you want to scale it into production, the supply chain doesn't really exist to support that production ramp. So both of these are some significant limitations with single laser systems. The pretty clear next step would then be to add more lasers, right? If it's too expensive because it takes too long to print a part, we'll just add more lasers. And in doing so, drive the part cost down. So if I put a second laser on a system, I may increase the system cost by something like 20%, but I can almost double the throughput. And in doing so, the part becomes significantly cheaper. It also helps with some of the supply chain constraints because now you have a supply chain that can produce twice as many parts. Adding 4 lasers is, again, a good way to reduce costs and kind of address these issues even further. But one of the things that's not often talked about as you look at these large parts in production is the quality issues that come with transitioning to multi-laser systems. So you can absolutely build parts faster, but because of the multi-laser nature and the fact that the lasers have to work together to build one part, the quality often suffers as a result. This is a real problem with a lot of aerospace customers that we have because they're trying to produce big parts and to transition these into production. So if you look at like the new space is a really good example of this. People are printing rocket engines, right? There are a lot of companies, especially in LA, just within 20 miles of here, that are producing rocket engines. And they're trying to print them because this is a really good way to reduce the weight of the part, to increase its performance by having these complicated cooling channels internally, and to scale quickly, to basically go through the development cycle as quickly as possible. And we have one customer that I was talking to is a really great example of this. They bought a big format system with 4 lasers because the goal was, I'm going to make big parts and I'm going to make them fast and we're going to get these things to space. The problem they ran into is that when you're printing these very thin walls with multiple lasers, where the lasers overlap, if your overlay region is not dead on, you start to get holes in the walls of the parts. And when you're trying to separate a combustion atmosphere from the fuel, this can be very problematic if there are holes. So this customer actually ended up getting the large format system with a single laser also, just to make the large parts. And they now use this multi-laser system as essentially 4 small systems. They produce large batches of small parts on the multi-laser system. And I think this is a really good example because it just highlights how up until now there's really not a good solution for producing large production quality parts, especially in industries like aerospace, oil and gas, automotive. And that's one of the things that Velo3D addresses with our system. So I'm going to go into a little bit more detail about how we address the quality aspects of large parts and also how we address the cost and the throughput aspects when you're working with multiple lasers. The first thing that I want to go over is kind of what we mean by laser-to-laser alignment. So when you're printing a part with multiple lasers, what I'm talking about is essentially the accuracy with which you can point at the same spot on the build plate with both of your lasers. Okay? And the reason this is really important is that if you aren't pointing at exactly the same spot, it becomes pretty evident in the part. You get shifts in the part, and this causes mechanical property defects, this causes surface defects that will reduce the part performance. It's a real problem for fatigue if you're in a fatigue-limited setting, and often it won't meet dimensional specs. So as an example, in this part, we've artificially offset the alignment of one laser by about 100 microns. And so we build one cube with a single laser, and then we build the cube on top of it with a second laser. And because there's an induced offset, you can see that there's a clear shift in the part. And then when we go back to the first laser, the shift goes the other direction. So if this were a part that you were trying to have meet some dimensional specs, it would most likely fail. The other aspect of it is, of the overlay, is that the surface quality can suffer as a result of the overlay not being in spec. And this is a pretty busy chart that basically the takeaway is on the bottom row, we have offsets of plus or minus 50 microns in our laser-to-laser alignment. And if the offset is 50 microns or below, in general we find that the mechanical properties are good, the surface quality is good, and that the part is deemed acceptable at the end of the day. But if the alignment is not within 50 microns, you get a lot of defects. You get surface roughness, you have mechanical property defects from lack of fusion porosity within the part. And the part, generally, for a production setting and something like aerospace, a highly regulated environment, it's not going to pass the inspection. So this helps us to establish kind of a baseline of what we need in terms of alignment to have a part considered successful. Yeah, sorry. So these are cones that we build at different angles, right? So we have, these are overhanging 35 degree, 45 degree, up to a 90 degree vertical wall. And we're doing a surface profilometer measurement, so an optical measurement of the surface quality to measure the roughness of those parts. And on the kind of the y-axis here, you have the different offsets. So plus or minus 50, 100, 150. So you can see the effects of overlay differences on the surface quality. Does that make sense?
Yeah.
Okay, yep. So to further illustrate some of the advantages of Velo and our in-situ overlay and multi-laser performance, we're going to look at printing a part. Just kind of go through a thought exercise of printing a part. And we're going to choose the worst possible part to print, which is just an ingot. We're going to print a cylinder of Inconel in this case. So this is a cylinder that's 250 millimeters in diameter. It's a 10-inch diameter and about 16 inches tall. It's a massive piece that you would never, ever want to 3D print. But it serves to illustrate some points here. For our system, this would be about an 8,000 layer build. We run it at 50 micron layers, so it's 2,000ths of an inch. And this would probably take about 8 days. This would be a long print. The reason that's important is that a lot of these parts are long prints, right? In a lot of aerospace or oil and gas or pump applications, you're building very tall parts, and they often take many, many days. Sometimes we've heard people quote 30-day builds, not entirely out of the realm of possibility. And this becomes an issue because your galvos and the way that they are aligned can change throughout a build, right? So depending on the thermal characteristics of the build chamber when you do your alignment versus while the system is running, you can have a pretty dramatic shift in your overlay. You also, the galvos are essentially motors with a rotary encoder and a mirror on the end of it. And those encoders can drift also. So if you're looking at a very long build, this is something that you have to be pretty aware of because it can cause your parts to get worse and worse as the build progresses. So even if you start out with a perfectly calibrated system and you're splitting the part in half, your first layer may look like this, where everything's lined up. You have core as the lighter color and contour as the darker color, and you have one laser on top and one laser on bottom. So everything's perfectly lined up. By the time you reach layer 8,000, they could be completely misaligned. And this is something that you wouldn't know while you're printing a part until you finish and pull the part out at the end of the build. So it can be a very costly quality escape. At Velo3D, we've built a system into the machine that allows you to calibrate the machine before you start a build with on-system tools, so you don't need any auxiliary equipment, you don't need any other equipment to do this calibration, and then to maintain that calibration during the build. So one of the really nice things about the machine is that it has essentially one-button calibration functionality. So before I start a build, I can click the button that says calibrate, and it runs through a short 10 to 15 minute process to calibrate the optics of the system. This is really helpful because it eliminates the need for a field service engineer to come in. It makes the calibration something that can be done by operators, and it means it's something that you can do every build as opposed to doing it on a PM schedule every 3 months or every 6 months. So this is a good place to start, but it doesn't solve all of the issues because you could still have drift, you could still have changes in the thermal characteristics of the chamber. So you also need to be able to check this live. So we also built the ability in to, on every layer if you want, measure the laser overlay, measure the laser to laser alignment, and compensate for that live during the build. So this is an example of a plot where we're looking at one of the lasers and its XY calibration. And so we start the build and it starts to creep out of spec because the system's heating up, the dimensions of the chamber are changing, and it would slowly go out of spec and you'd start to have a shift line. And we turn on our automatic calibration here. You can see the orange line where we turn on the calibration, quickly jumps back into spec, and then it maintains it through the rest of the entire build. And this is something that can maintain the calibration to within 20 microns. So we're well within our spec for mechanical properties, for surface defects, and for part quality at the end of the day. And we have a challenge that we like to give to anybody who's willing to take it. To come to our booth, we have several tall parts. We have one that's almost a full 16 inches to come and try to find the overlay. Because one of the things that we're pretty confident in is that the overlay is it's invisible, essentially. You can't tell the difference between the parts that we're printing and on our multi-laser system versus one that was printed with a single laser system. And to further illustrate that, except on a much, much smaller scale, this is the same block printed, but with the overlay correction turned on. So again, it's essentially indistinguishable from a part printed with a single laser. So this addresses a little bit of the quality aspects of multi-laser parts. The other aspect is really around productivity. Because if you have 2 lasers and one of them's running at 50% utilization because of some scheduling issues, you're not really realizing the full benefit of a multi-laser system. So one of the things that we try really hard to do is to optimize so that you're actually running 100% of both lasers all the time. And this is the real way to realize the benefits. And it may seem like a pretty straightforward problem, right? You just turn it on all the time, right? Don't schedule it so the laser's off. But there's a really important consideration that you have to take into account when you're working with multi-laser systems. And this is somewhat complicated with 2 lasers, but it becomes much more complicated with 4 and 8 as you scale up. This is a really important consideration. And that consideration is don't shoot the smoke. This is a rule in multi-laser processing. The smoke that comes off of the process is condensate. It has metal particles in it, metal vapors, and if you shoot through it with one laser, you're reducing the amount of power delivered to the bed. You have to have a certain amount of power delivered to the bed to melt the material thoroughly. And if you don't, a lot of times you'll end up with lack of fusion defects, which is one of the biggest causes of mechanical property deterioration. So, very simple rule, don't shoot the smoke. And if you're looking at multi-laser systems in operation, this is always a fun one to check for because you can watch while they're building and see where the lasers are going. And a lot of times they'll end up in eye formation. They'll all be directly downstream of each other, which is not where you want to be. So we have a relatively simple way of approaching this that's very effective. This is a plot of an actual build of a cylinder as a function of time through the layer. So we start on one side with red being where the layer starts and purple being where the layer ends. And we have two lasers on our system, two 1 kilowatt lasers. So one of them will start at the lower left and one of them starts just above the middle line of the part. They both proceed upstream, and we do core decomposition, so we make our core process broken up into blocks, and that's why you see these squares in the print. And these march upstream so that they're never operating kind of in a downstream fashion. And once you reach the end of one swim lane, both lasers then reset at the same time to be back at the beginning on the downstream side and move back upstream. So in this way, you can have both lasers operate essentially 100% of the time and never be downstream of each other. So it's a pretty straightforward solution, but it's been very effective. And you can imagine that with a more complicated part, this becomes a little bit more interesting. This is a pretty basic example of how to do this. But the goal here, again, is 100% utilization of both lasers all the time without impacting the quality in a meaningful way. So I also brought with me a part that is representative of some of the parts that we're building now. So this is an aerospace application. This is a microturbine, actually, or an APU, auxiliary power unit for like a jet engine. This is a titanium component built on our machine. So it's about a 10-inch diameter. This is built with both lasers. And this is really important because this company, KW Micropower, based in Florida, was looking for a solution to print a very challenging geometry. And if you look, this part has flow paths that go basically through the part and then come out the bottom. So it's pretty interesting internal geometry. The problem with printing this on a multi-laser part is if you aren't accounting for the overlay, I can print one of these parts, but these guys are going into production. They plan on producing 100 to 1,000 of these over the next 2 years. And they had no solution for production. Only when they came to Velo and were able to kind of realize the benefits of the multi-laser processing with our quality control, were they able to achieve both the cost reductions they needed to go into production, as well as the quality and the geometric capabilities to actually make this a realizable product. So this is one of our shining examples of how you can benefit from using Velo's multi-laser capabilities. So. Any questions? I can pass this out so you guys can. Yeah, it's been machined. All of the shiny surfaces are machined surfaces to interface with the rest of the engine. Other than that, there are no real supports removed. The inside of those passages had no supports in it. What's that? It's actually slight oxidation from the stress relief process. So it goes through a heat treat process, and it changes the patina of the metal a little bit. After you print it, you stress relieve it, and then cut it off and then machine it, essentially. It's in a furnace, so we put it in a furnace at 1,000 degrees and let it sit for 9 hours. No, it's 100% dense before it goes in there. It's just so that when you cut it off, it doesn't try to deform. So it's printed, there are internal stresses in the part as it prints, and when you cut it off, you don't want it to deform the part, so you go through a stress relief cycle before you cut it off the build plate. It was welded to the build plate. Yep. That one was not free floating. Unlike our chainmail, not free floating. No, those were all open. So, all of the machined holes? Yeah. The threaded holes were all done afterwards in a machining step. So I think on the calibration side, it's pretty straightforward to communicate the benefits. Like, people recognize that it's better to have a calibrated system and to maintain that calibration. I think Our system has the capability of operating in closed loop control, so we can monitor the melt pool and adjust our laser power in real time. And that's a more interesting discussion because there are a lot of industries that don't want your machine to change parameters on the fly. So some people are good with, some people are a little more hesitant about. Thank you.